In general, hardening is quite a complex procedure, and it is used for a fairly wide range of materials. But we will examine hardening using metals as an example and see what happens in the metal. In order to fundamentally understand this method, we took a piece of iron, plunged it into a bucket of water. The iron was previously heated, it sizzled and bubbled there. We took out the iron, and it became stronger. That's basically the whole hardening process. That's if we speak in simple terms. But here we need to pay attention to one very important characteristic. We are not taking a simple piece of iron, it's not pure iron, it's steel. Let's recall how steel differs from iron. Pure iron is pure ferrum, while steel is an alloy of iron and carbon. So when we talk about steel, we are talking about at least a two-component system consisting of iron and carbon. The immediate question arises, what happens if we harden pure iron? Yes, generally speaking, nothing will happen because the properties won't change, except that due to the work hardening effect, the piece of iron we placed in the quenching medium will become stronger. But the actual hardening effect that we are talking about won't occur. During hardening, a more complex physical process takes place, which we are approaching, and this physical process is only possible in materials composed of multiple components. The very steel we are talking about consists of two components, with iron and carbon being in a specific state. The state of the alloy can vary greatly, and information about this state is provided on the iron-carbon phase diagram. Yes, that very frightening and terrible one, in which everyone constantly drowns, and which in principle drives you crazy just by looking at it. But we are interested in the simplest example, and we will take ferrite. What is ferrite? It is essentially steel. But what kind of steel? This steel is very simple. Ferrite is a solid solution of carbon in alpha iron. So many new words, aren't there? Let's break it down step by step. A solid solution is a state that results from mixing two components. We have a liquid solution, for example, tea with sugar. And we have a solid solution, for example, iron with carbon, and essentially that's it. I think it's clear that when we talk about the solid solution of carbon in alpha iron, we imagine alpha iron having a BCC lattice, and envision carbon that fits inside this lattice. In order to perform quenching, we need to heat the material. Why is heating necessary during quenching? How can it affect changes in properties? I imagine that very cube with carbon embedded in it, which we just talked about, and we imagine that we start heating it. Various processes will begin there. Energies at the grain boundaries will change. Energies in dislocations will change. Everything will spin and turn, and this whole thing will slowly start to melt, but before it begins to melt, rearrangements will occur. And in general, the iron-carbon alloy has a very interesting property when heated. There, ferrite can transform into austenite. This is our solid solution of carbon in gamma ion. How does gamma ion differ from alpha ion? It is practically the same. We have the same carbon content, but the structure of that very crystal lattice, the minimal one, is different, which essentially represents the main lattice of our sample. In other words, when we heat a steel billet to a certain temperature, within this steel billet, one type of crystal lattice transforms into another type of crystal lattice. This is essential. Now remember this and pay special attention to it. We have undergone a polymorphic transformation. A polymorphic transformation is a transformation where one type of lattice turns into another type of lattice. But where does the carbon go? But as long as our process is slow, as long as our process occurs in this manner, gradually we heat everything thoroughly, we maintain everything carefully. The carbon freely redistributes itself across the new lattice through diffusion processes and is rearranged in the new cubes that have formed. Thus, it turns out that heating during quenching is necessary for us to be able to restructure this lattice, to initiate internal processes, and to achieve the polymorphic transformation. Well, why on earth do we need this polymorphic transformation? Is it really necessary at all? How can it affect the properties? So nothing is clear to us? Well then, let's move on. So far, everything is correct, and we are heading in the right direction. And then, we need to cool it all down quickly. One might think that cooling is needed to fix the structure we have obtained. In fact, cooling is needed to break this structure to smithereens. When we throw all of this into water, the transformation process starts again. But the process doesn't happen as calmly and slowly as it did with normal slow heating. It happens instantaneously because the cooling is very rapid. And during this rapid cooling, the growth of the crystal lattice occurs. Moreover, the growth and change of the crystal lattice, its restructuring most importantly, happens at speeds close to the speed of sound. The lattice tries to restructure, and our FCC, which you remember from the picture you saw, transforms into a BCC, a simpler structure than the FCC, and there is less space there. And of course the effect is somewhat like trying to enter the subway. You know, children used to play a game called A Place in the Sun. It's when everyone runs around in a circle and there are chairs, and there are always one fewer chairs than there are children. So, the carbon from our example starts to press on this lattice from the inside, And when the lattice restructures, the carbon needs to find somewhere to go, and it gets stuffed into various parts of the crystal lattice and stays there. As a result, the crystal lattice got affected. Our lattice was cubic, but it became this rhombohedral one. It expanded. In general, it's like a subway car. In the morning, everyone tries to squeeze in, and they do so in such a way that sometimes someone gets thrown out of the window, or legs are sticking out, or someone's bag gets caught. That's exactly how carbon behaves in steel. When we rapidly cool our steel sample, the transformation from one lattice to another begins again. And in the end, we get a BCC with carbon insertion, but it's not as uniform as it was under calm conditions, but rather like this, as if a tractor drove over it. And basically, we find that martensite is a hard, supersaturated solution of carbon insertion in alpha iron. Why did the word supersaturated appear? Because when the structure was being rearranged, the diffusion processes, meaning free redistributions, couldn't occur evenly, and the carbon atoms started to be crammed in wherever possible. When this process occurred, supersaturation happened. Why do we have alpha iron again, and not gamma iron? Because when cooling occurred, we had steel. Thus, it is structured so that the lattice transformation, the polymorphic transformation, still had to take place. And now let's try to describe the quenching process anew, which we formulated at the very beginning. There we said that you need to take a steel sample and plunge it into cold water after heating it to certain temperatures. In this steel sample, the iron was initially in the form of an alpha crystalline lattice, and carbon was present there as a solid solution of interstitial carbon in this very alpha iron. Then we started heating this sample at a certain rate. Heated it to the critical temperature, where the transformation of one lattice occurred, from BCC in charge characteristic of the alpha phase to FCC, characteristic of gamma iron. And there, our carbon also redistributed, resulting in a crystal represented by an FCC lattice, where we have a solid solution. The incorporation of carbon into gamma iron, this occurs at high temperature. Now we cool all of this down. As we start cooling, what happens is like a morning rush hour, atoms and molecules start moving back and forth, the diffusion process is slow and gradual, making it impossible to rearrange properly. Nothing works out, so congestion begins. Due to the properties of steel, the lattice changes during cooling again from FCC to BCC, and this rearrangement occurs because atoms and molecules are bustling around. The lattice cannot settle properly, and everything solidifies as if fixed, resulting in new bonds and new types of structures. And this time we obtained a structure called martensite. Martensite is a supersaturated solid solution of carbon in alpha iron. Notice that once again gamma iron has transformed into alpha iron. The most important thing to remember here is that this type of quenching is called quenching with polymorphic transformation. That is, the lattice transforms several times. The crystal structure of our steel sample changes from one type to another. Now let's answer the main question we posed at the beginning of the video. Carbon is distributed inside in such a way that I would say strengthening occurs. Of course, we also experience mechanical hardening. This hardening occurs at the micro level, but it happens, and because of this, we have an increase in the number of dislocations, an increase in the number of obstacles for these dislocations, and an increase in the strength of such samples. And the third reason is that we have a huge number of obstacles that hinder the movement of dislocations. And we remember that the dislocation theory is in charge, and the destruction of metals is described precisely through dislocations. But I will slightly disappoint or perhaps please you, as it turns out there is another type of hardening. Hardening without polymorphic transformation. And it is precisely the hardening without polymorphic transformation that is usually represented by those who know the word hardening, know that the metal is strengthened because of it, but do not know why. That's exactly where it happens that we essentially fix the structure. We heated it up and we got this mixture. Then it was quickly cooled. The diffusion processes did not have time to occur, and since they didn't have time to happen, everything solidified in the state it was in.